4, where we will talk about some very important laws of logarithms and the change of base formula. So let me bring this back. So this is the section 4.4. So these properties, I guess after you practice with a few of these problems, you'll remember them, whether you decide to remember them or not. You will automatically remember them. But if not, please make sure that you memorize these, because they are crucial in solving logarithmic kinds of equations and exponential type equations. These are very, very useful properties. So before we begin, though, let me remind all of you to please skim through the section 4.4 before you watch this video or before you attend the class. And then when you attend the class and during the time when you watch the video, take notes. Take notes about what you think is a question for you. If the video is not addressing a certain question you might have, write it down and then ask me about it later. Or if you think there is some important point that is being covered and you might forget it, then you want also to write those down and remember them for the duration of the semester and beyond, in case if you are taking higher and higher levels of mathematics courses. And of course then, as you read the book and as you rewatch this video, please make sure that you pause the video where applicable and solve problems on your own before you see my solutions, or review the solved problems in the book in section 4.4. Solve those problems without looking at the solutions given in the book, and that way you develop your own learning, your own ideas about these problems as you move through the course, which is very, very valuable. You're not here to memorize my ideas. You're here to develop your own solutions and your own thinking about this topic. And then, of course, complete all the homework assignments by the due date. You do not want to procrastinate on completing these problems, and time is of an essence. As we cover these sections, the homework assignments should be completed soon after. And then review all the previous material that we've covered in this course to keep them fresh in your mind, especially those of you who will be taking much higher math classes later, 300 level and 400 level math classes, which are those of you who will be majoring in science and engineering. Okay, having talked about that, then these properties, on one side, these are very, very similar properties, but one side looks at logarithmic properties for log functions or log expressions. The other side are the equivalent properties for the natural log one, for the natural log function or expression. Okay, and they are very, very similar. So and in each of these equations, we can go backwards. We can go either from left to right or right to left. For example, the first one, I'm beginning, instead of equality, I'm using double-headed arrow to indicate that you can either go from left to right or right to left. And that goes for both sides. Okay? So the first property says that if you have the log of a product of two entities, then you can break that up into addition of log of each of those entities. So multiplication, the importance of this is that a multiplication problem can be changed into an addition problem, and that same property is valid if you have a natural log expression. Here, we're saying that if you have the log of two terms in parentheses that are being divided, then you can change that expression into the subtraction of logs of those two, the term in the numerator and the term in the denominator. And the same property goes for this one. Okay? The other property is if you have, okay, so this is important. So if you have the log to some base b can be anything, of k over L, something like that, that's not equal to, this is very important, we're saying the left-hand side is not equal to the division of log of k over log of L to that base. So we can go from a division problem to a subtraction, but that left side is not equivalent to this. Okay? So you could not say log of k over log of L to that base b. That's not a valid equation. But we can go from here, log of k over L, to a subtraction problem. And vice versa. If we have a subtraction problem like that, we can rewrite that expression on the right in terms of what you see on the left, log of the ratio of k over L. Okay? All of these properties are very, very important. You'll see. We'll do plenty of examples, and you'll see how useful these properties are. Then the next property says that if you have log of some value to some base, and this value, the argument, has a power, the argument k has a power, you can bring this power in front, put it in front, and then have c log of k to that base, whatever it is. Okay? These properties are extremely important when we start solving logarithmic equations. Very, very important. Without these, we couldn't solve them. So the equivalent of this property also exists here, that if you have log of k to some power c, this power can be brought in front and multiply itself by the rest of this. So c natural log of k. Okay? So then we talked about that. And we talked about, so this is basically saying, this next property is saying that, so we already know from the previous property that k can come in front. So, and become k log of b base b to some base same b. So in other words, this is what it's saying. So what this is really saying, it's saying this. If you have log of any number, let's say x, to some base x, that's equal to 1. Okay? That's always equal to 1. If the base is equal to the number that you take the log of, then you get 1. And that makes sense because last video, we learned that the log and natural log functions generate an exponent, right? So we know that is the exponent of some base. To what base? To base x. So x to that power is equal to this result, x, which makes perfect sense, right? We can't argue with this. So that's the exponent because log and natural log functions generate or produce an exponent. So the other side of the equality symbol is always an exponent. That is the base, and that is the result, right? Result. Okay, so this base to that exponent is equal to that result. And it makes sense. So if you have log of 5 to base 5, guess what that is equal to? 1. If you have log of 4 to base 4, guess what that is equal to? 1. If you have log of 10, what is that equal to? Last time we said if we don't write the base, if we don't write it, what is that equal to? The base is equal to 10 if we don't write it. You can write it, but by mathematical convention, it's mostly not written if it is equal to 10. So what is that equal to? 1, right? using the same idea we talked about here. So log of any number to the same base as equal to that number is equal to 1. So that is what that is saying. This property is really saying, because from the previous property we know that k can be brought in front. But when you bring the k in front, then you end up with k times log of b equals then, so then the whole thing, this is equal to 1 times k is equal to k. In other words, log of that is equal to k, bring this in front using the property, log of b to b, but we just discussed that that is equal to 1. So k times 1 is k. Okay, that's what that property is saying. Okay, the same thing is that if you have a number raised to a log expression to a base equal to the base of the log function, and then that all of that is 1, so then that expression equals k. In other words, this cancels itself to just nothing, 1 times k. So in other words, if we have, let me put this so you can see it like that. So for this, if we have, say, 5 to log to base 5 of 9, that is equal to 9. Because we have a base 5 raised to some exponent log of base that is equal to this base of 9. So it's equal to 9. Or log of, 8 log to base 8 of 15 is equal to 15. Because this whole thing cancels and we end up with just 15. That is what that property is saying. Okay. The next part, on this side, I almost forgot about this side. Very, very useful properties we have. First of all, that is the same thing as that one, right? So if natural log of k to some power, you can bring that power in front. Okay, you got to be careful when you apply this property to log or natural log expressions that have a power more than one term. So if this c was c plus x, then what? Then what happens? So we get to examples like that, so you'll see how to avoid any difficulties with those kinds of problems. But we got to be careful when we apply these properties. Okay? Then this one is, we know, using the previous property, x can come down and in front. So x times natural log of e. Okay? And I guess I have to discuss this and this property at the same time because they're so related. This one, log of 10 equals 1, and that one are actually, and that one actually, are very, very related. These are very, very related properties. Not to in between natural log and log, but also within each category. They're very, very related to each other. Okay, so here, log of 10 equals 1. But log of 10, notice the base is missing. Log of 10 to the same base as 10, it's equal to 1. It's the same property almost like that. Okay, but that's more than this. But this property makes use of the fact of what we just talked about. Log of any number to the same base is equal to 1. Log of 8 to base 8, 1. Log of 9 to base 9, 1. Log of 50 to base 50, 1, and so on. Okay? So notice that the base is not written, so we know it's 10. Then log of 1 equals 0. I mean, you can verify these on your calculator as well, but log of 1 equals 0. I mean, we can quickly do that here. So log of 10, 1, right? We would expect to see that. And this is log of 1 equals 0. Log of 1 equals 0, right? And last time we learned that log of 0 is what? Do you remember? Log of 0 is undefined, error. Log of a negative number is undefined. Log of 0 is undefined. We always can calculate the log of a positive number. Okay, log of negative numbers, and 0 is undefined. Please remember that. Okay. So on this, oh, by the way, so here we say that log of, we learned that if you take the log of the product of two numbers, that translates into sums of log, the sum of the logs of those two numbers. So you can go from a multiplication problem to an addition problem. But we cannot go, and we can go backwards. So we can go from this addition to multiplication. But this property says that you cannot go from addition to addition. Okay? We can go from addition to multiplication, and from multiplication to addition. But we cannot go from addition to addition. Okay? I hope this is making sense. These are just rules. So once again, we can go from a multiplication problem involving log, to an addition of expressions involving log. But we cannot go from addition to addition. We can go from multiplication to addition. We can go from division to subtraction. But we cannot go from addition to addition. Okay, so on this side, natural log of e to the x is equal to x. How is that possible? This property is very, very related to this property. These two properties are very related, because by the previous property, that means x can be brought down and in front of this natural log expression, right? But when we do that, natural log of e equals 1. So x times 1 is x. Okay, so remember these two properties, and let me go to my scratch paper here. This is saying that if you have natural log of e to the x, so what can we say about that? Well, we know that this exponent can be brought down and in front, so x natural log of e. But we do have a property that says natural log of e is equal to 1. Why is that? Well, do you remember that any natural log has base e? So natural log of e to base e is 1, right? Because this is an exponent to this base gives us this result. E to first power or exponent is equal to e, which is that result. Okay, so natural log of e is equal to 1. And that's what we have here. So e, some base to a natural log, which has base e, again, it ends up being the same property as this one, I believe. Yes, this one. So these two properties are related. This one is for the log expressions, and this is for the natural log. Okay? Which last time we looked at the natural log, if in case, I hope you remember this, the previous lesson, that log to base e of x is equal to natural log of x. So that's what natural logs are. They are logs to base e. Okay, so you show me a natural log, I already know the base is e. Okay. All right. So now we talked about that. Natural log of e equals 1. We talked about that. Natural log of 1 is equal to 0. So, I mean, we can look at these on the calculator. So let's take natural log of e equals 1. Let's see if we get that on our calculator. So natural log of e, let me put in e to raise. So we expect that to get 1. There it is, 1. Let's take natural log of 1. We expect to get 0, right? 0. Okay. So the change of base formula, which is that one, very important. I want to remind you that these properties came to us or come to us from centuries ago. So if you have properties like this, in a day where there are no calculators, there are no computers, so that's how important these properties are. They help us work out problems. Not all problems, but a large portion of logarithmic and natural logarithmic problems without the use of a technology. In fact, as you know, in this class, you are not allowed to use calculator during exams, at least when you take the class on campus. Okay? If this course is online, then you can use it, I guess. So the change of base formula is one of those important formulas that comes to us from centuries ago again, and it simplifies solving log functions and logarithmic equations a great deal. It basically says if you're taking the log of some quantity to some base other than 10, okay, and other than 0, of course, if that is 10, then we have, if that base is 10, then we have our own formulas. And we have in today's calculator, you have a button for it if you want to use technology. But in case that is not available to you, the technology or other tables, we used to have tables for log functions. And so you can take that log and write it as a ratio of the log of x divided by log of b. And it's the same thing with the natural log. So the same property applies to natural log functions. So you can write that as a natural log of x divided by natural log of b. So we're saying, what that property is really saying is this. If you have log of, say, 3 to base 8, let's say, that is equal to, you can rewrite this as a ratio of log of 3 divided by log of 8, both of them to base 10. Okay, I didn't write it, but you can write it, base 10, base 10. Or you can say that is equal to natural log of 3 divided by natural log of 8. This greatly simplifies things because, as I said a few seconds ago, to calculate log values before the days of calculators, commonplace calculators, they used to have tables, graphs. So and all of these graphs were based on logs of 10, log base 10. There were other tables too, but if you could use one table or one graph of logs to base 10, that would greatly simplify calculations of logs of numbers to other bases. Okay, so this is one way you could simplify that. So if you have, suppose you don't have the graph, or they call them tables, they were graphs, but they call them tables, of logs of numbers to base 8. Suppose you're missing that graph, but suppose you do have the logs to base 10 graph, the graph for that one, then you could easily find, from the graph, you could find the log of 3 and log of 8, from the graph to base 10 and then divide those numbers and find the log of 3 to base 8. Okay, so very useful formula again. Okay, so now that we've talked about these properties, please, it's not my favorite comment to ask you to memorize formulas and properties, but in this case, it would help you a great deal when you solve problems involving logarithmic functions if you have these properties memorized. Okay, so any 10 or 15 minutes you spend on memorizing this, it is well worth it. Okay, so let's look at these examples. Please pause the video, give it your best shot at solving each of these, and then unpause the video and come back and see my solutions. Okay, I'm counting on you that you take that advice and write down your own solutions. Your solutions are far, far more important than mine, okay, because your solutions are coming from your mind, which is what you're trying to develop in this course. Okay, so I'm assuming you've done that and now you're back. So let's rewrite this expression. We want to evaluate this. Let's rewrite it. And we want to do this without a calculator, okay? With a calculator, it would be easy, right? We could apply the change of base formula right away, and we could take log of square root of 27 divided by log of 3, and we'd get the answer with a calculator. But we're trying to do that without a calculator. Okay, so let's rewrite this with rational exponents. So log to base 3, instead of, before that, I want to write this as square root of 3 cubed. Okay, so I just rewrote this like that. Then let's rewrite what we have under the radical in terms of rational exponents. A few sections ago we learned, or much earlier in the semester, we learned how to do that, right? So log to base 3 of 3, I'm going to rewrite this as a fractional exponent, 3 halves, right? The index, when it's missing here, that means it's 2. So 3 to 3 over 2 power. Okay? Then, using this property, we know that the exponent can be brought down and in front, right? So that means I can move this 3 halves down and in front. So 3 halves log of 3 to base 3. Okay? But we already learned that if you have the log of some number to a base equal to that number, what is that equal to? That is equal to 1, right? This piece is equal to 1. So 3 halves times 1 is equal to 3 halves, or 1.5, right? So we were able to solve that expression without the use of a calculator, just using those properties. Okay? Imagine how useful these properties were several centuries ago when you didn't have calculators. Okay, so this one. Now this is a subtraction problem, right? We want to evaluate it. We know we can write a subtraction problem in terms of a division problem. We can either convert a division problem to subtraction or convert a subtraction to a division, keeping in mind that this log of k over L is not equal to log of k divided by log of L. So division to division is not allowed. Division to subtraction is the property we have. Okay, so let's do that. And by the way, we can do this because they're both log expressions are to base 4. If one of these had a different base, like 2, like 10, we couldn't apply these properties. So all of these properties we looked at, the base has to be the same for different logarithmic expressions. Okay, so we can rewrite this as a division of two numbers. So log to base 4, notice both bases are 4, in parentheses 192 divided by 3. Okay, so I'm applying, to do this, I'm applying this property going backwards, going from right to left. We have this, I went backwards to get this. Okay. All right. So now, that is an easy number to divide, right? What is that equal to? We have log to base 4 of, that is 64. 64, right? Okay. So 64, can we write this as a number raised to, as a number equal to 4 raised to some number? We can, right? We can definitely do that. So 64 is equal to 4 cubed. So let's write it that way. So we can write log to base 4 of 4 cubed. Okay? Now, we have a property that says, hey, if you have an exponent like that, in relation to a log expression, you can bring the c or exponent in front and down and in front, there. See where c was on this side? Now where it is? It's in front and down. And k has lost its exponent. So we can do that. Let's do that. So this 3 can come down and in front, right? It was here. Now it can be brought down here. Then we are left with log of 4 to base 4. But we just talked about that every time you have a log of some number to the base that is equal to that number, that expression equals to 1. Right? So then we have 3 times 1 is equal to 3. Okay? I'm sure you are quickly seeing how important remembering these properties are. Because if you don't remember these properties, you can't even begin this solution. You can't even go from here to here on an exam if you don't remember the properties. Okay? The coordinator might allow the use of notes, but I don't know that at the time I'm making this video. But if the coordinators of this course allow the use of notes during exams, then you're more welcome to use them. If I announce it, then you can. But even with the notes, it's better to remember them because you'll solve these problems much faster, okay, during an exam. Okay, so next we have, they want us to evaluate this expression. Well, this is a series of subtractions, right? So let's convert this first subtraction to a division problem. We know we can do that, right? We know we can go from subtraction to division and from division to subtraction. So let's use that property for the first two. So I'm going to write log, and notice the bases are the same. If this was 3 and that was 10, or this was 8, that was 3, we couldn't do this. But the base of all these log expressions is equal to 3. So we're allowed to do this. So log to base 3, and we're going to change the first two into division. So 100 divided by 18, and then minus that last log expression. Okay? So now we can use that property again for these two, because we have a subtraction in between, right? So I would simplify this if I could, but maybe we can, right? Because they have factors of 2. 100 has a factor of 2. 18 has a factor of 2 as well. But that's one way. But let's keep these numbers for now. We'll simplify them later. So log to base 3 of all of that divided by 50. So 100 divided by 18 divided by 50. Right? So we went from subtraction to division twice. So we applied that property twice, and we ended up with this. Now, in the previous sections, we learned how to quickly simplify complex fractions, right? We did that. We can do it again very easily. So remember what we said? The 50 has denominator 1, right? This denominator of 50 is 1. For complex fractions, we learned that we can multiply the values that are farthest away from each other and write them in the numerator times 1. Then multiply the numbers that are nearest each other and write the product in the denominator. So 18 times 50. And we've eliminated the complex fraction. Now let's simplify. So we have log 2 base 3 of 100 divided by 900, right? 900. So we can easily simplify that because that's just 1/9, right? That is equal to 1 over 9. But what is that equal to? What is 1/9 equal to if you write it in terms of negative powers? Remember, we don't like negative powers, so in the final answer, we always want to get rid of them, but in the middle of our work, we can use them to our advantage. But we can't have them at the very end. But in the middle, why not? So I'm going to write this 1/9 as 9 to minus 1 power. Okay? 1/9 is 9 to negative 1 power. If you write this 9 to negative 1 power with positive power, you end up with 1 over 9. Okay? So now let's write 9 in terms of some number to base 3 raised to some power. So we can write log to base 3 of 3 squared to negative 1 power. Right? We can do that, right? 9 is 3 squared. All right. So now we know that any power on the outside of a parenthesis will multiply itself by the power of the term inside the parentheses. So we can write log to base 3 of 3 to negative 2 power, right? Minus 1 times 2, minus 2. Now, we can write, we know the property that if we have an exponent like this, we can bring it in front, right? So we can do minus 2. That minus 2 comes down and in front. Log to base 3 of 3, right? So that whole thing, this piece is equal to 1. So minus 2 times 1 is equal to minus 2. And that's the final answer for us. Okay? So look at the power of these properties. We had that, which looks like a very complicated expression. Without a calculator, we are able to write down that that expression is equal to negative 2. Look at the power of simplification. That's why we ask you over and over to simplify your final answers, because simplifying unmasks the true expression that you have. What we had is not all that, it's just negative 2. Okay. So this next problem, it says use the laws of logarithms to combine the following expressions. So in this book, I guess they say combine, but in some other books they call this contraction or contract or make smaller. So that's what the problem really is asking us to do. It's asking us to use those properties or laws of logarithms to make this expression smaller, more compact. Okay, that's what we're being asked to do. Okay, so I have an addition here. We know from an addition problem can be rewritten as a multiplication problem, right? So let's do that. So log, and notice the base of all of these is 10, right? It's missing, which means they all have base 10. So log of before that. So before I multiply this, I have a number in front here which I need to write as an exponent. So let me do that. Log of 12 plus, put this back as an exponent, because we said that these properties can go either way. If you have an exponent, you can bring that c down and in front to get rid of the exponent. But if you have a number in front, you can put it back up. You can go this way and put it back up as the exponent. Okay? So here, I'm going to put this 1/2 as the exponent of 7. So log of 7 to 1/2 power. But log of 7, we know that rational exponents are very closely related to radical expressions, right? So 7 to 1/2 power is actually square root of 7. So let me complete this, log of 2. Then let's write this as log of 7. So log of 12 plus log of square root of 7. 7 to 1/2 power is equal to square root of 7 minus log of 2. Now let's apply that property that allows us to convert an addition of log expressions to a multiplication of log expressions. So log of 12 square root of 7 minus log of 2. Great. So we made this expression a little smaller. Now we have a subtraction. Remember, we have a property that says if you have a subtraction of two log expressions, you can convert it to a division between those terms of a log expression. So let's do that. So this is equal to log of 12 square root of 7 divided by 2. Okay, I just applied that property that I showed you. Now, can we simplify this? Absolutely. We can, because 2 is a factor of 12. So this drops out, we get 1. This drops out, we get 6. Right? So let's come up here. We can write log of 6 square root of 7. Can we simplify this anymore? No. We can write it as it is. Okay. I mean, they wanted us to write this as a smaller expression. That's what we did. We combined or contracted or made smaller this expression. Okay. That's what combining means. We went from here to here. Okay. Okay, so let's move forward to the next problem. Here, they're the same scenario where they're asking us to combine things. So we got to make this smaller. The first one is addition. The second one is subtraction of terms. So let's look at this first. We can write these two as a multiplication of terms, right? Remember this property? Addition can be written in terms of multiplication. And subtraction can be written in terms of division. Okay, so addition, let's multiply natural log of a plus b times a minus b minus 2 natural log of c. There's a lot we can do to combine this, right? A lot of things we can do. So the next step, remember this property? It comes up again and again. X plus y times x minus y. What is that equal to? That is equal to x squared minus y squared. Remember that? Those two terms are identical. The only different thing is the sign in between them. And if we're multiplying them, we get that. You can FOIL this. You get the same thing. But this, if you remember this special product formula, you can do this faster. If you FOIL it, you end up with x squared minus xy plus xy minus y squared. These two are equal and opposite. These two cancel out. You get x squared minus y squared, which is that. So that's why I say you can FOIL it, but if you remember it, it's much faster. So here we have the same scenario. So we have a plus b times a minus b. So then we can write log of a squared minus b squared. What about this? Look at this. We have a number in front, minus 2. Right? Or 2. What can we do? Do you remember this? This property? If you have an exponent, you can bring it and place it in front. If you have a number in front, you can go this way and put it up as the exponent. So if we go this way, c is gone from the front, and it's now appearing as the exponent. So let's apply that. So we can put this 2 as the exponent, minus natural log of c squared. Okay? Now, because we have a subtraction, we can write this as a division, right? Remember that? The subtraction can be written as a division of problem. So natural log of a squared minus b squared divided by c squared. Can we simplify this more? They ask us to combine this expression. Can we combine this or make this expression smaller than it is now? No. So this is the final answer. So let's box this like that. Okay. All right. So the next set of problems, they want us to do the opposite. They want us to expand. Use the laws of logarithms to expand the following expression. So we want to make them bigger, not smaller like we just did. Okay. So we have a multiplication problem here. We can open that up, right? We can open that up to if we have a multiplication, we can open it up, expand it into addition problem. Right? So let's do that. So this is equal to log to base 2 of 2 plus log to base 2 of x. Right? But we know log of any number to the same number to the base equal to that number is equal to 1. Right? 1 plus log of x to base 2. There we go. Okay. This B is a really interesting problem. So first thing, in order to expand this, let's rewrite this radical expression as an expression with a rational exponent. We know we can do that, right? Equals to natural log of z to 1/2 power, right? The power on the inside is 1. The index is 2 because it's missing, right? If it's blank, it means it's 2. So the power on the inside, which is 1, divided by the index, which is 2, gives us that. So all we did, we rewrote an expression using radicals as an expression using power. Okay, so let's continue. We have a property that says, hey, if you have a power of log or natural log expression on this side, you can bring that power in front and get rid of it as an exponent. A lot of times this hugely simplifies natural log or logarithmic expressions. Okay, so 1/2, we brought it down, 1/2 natural log of z. Can we do anything else to expand this anymore? No, this is it. So that's the final answer for that. Look at that, part C. Again, I hope that you are pausing the video, writing down your own solution, and then unpausing the video and looking at my solution a few minutes later. Okay, I'm hoping you're doing that. If you're interested in learning this, and I know you are, you need to do that. You need to take the time and write down your own solution first. Don't memorize my solutions. That's not learning. You gotta write down your own solutions. Please do that. Okay, so I'm assuming you've done that, and now you're back. So this is to begin with, this is a division problem, right? And we know we can write a division problem as a subtraction problem. When we have log, of course, right? We couldn't do this with other expressions, but we have log. So log to base a of x squared minus log to base a of all of that, y, z cubed. Okay? Now look at this. We can do a lot to expand this, to make it bigger expression, right? Look at this power 2. What can we do with it? We can bring it in front, right? Let's do that. So 2 log of x to base a. Okay, we're opening this expression up using those properties. Now that is an interesting expression. We have minus log of this of 2 terms that are being multiplied. When we have multiplication, we can write them as addition. So let's do that. But we got to be careful. When we open this up, this second term, which is in multiplication form now, when we open it up and write it in terms of addition, we're going to end up with 2 terms as opposed to 1 which we have now. This minus in front is being multiplied or distributed to all of this. So if we end up with 2 or more terms, this minus belongs to all of those, so it should distribute itself to all of those. So what I'm saying is that when you put the minus, before you open this up and convert it from multiplication to addition, you must put a bracket here. Okay? Because you're going to end up with 2 terms, and this minus doesn't just belong to the first term, it belongs to both of those terms. Okay, so log to base a of y, now we're going to open this up with addition, right? The multiplication goes to addition. Log to base a of z cubed, closed bracket. Many, many times I've seen people forget this bracket, these brackets, they forget. So what they end up with, this minus ends up belonging to just this first one, log of y to base a. And the other one stays positive. But look at this. This minus, this bracket suggests the correct path which means this minus belongs to any expansion of this. That means it belongs to both of these. So this minus has to distribute itself to this and to this. Let's do that. So 2 log of x to base a minus log of y to base a minus log of z cubed to base a. See, this minus distributed itself to both terms. Again, if you forget these brackets, you end up with this, putting this minus just for that. You forget, and your final solution is not going to be right if you forget to distribute this to the other one too and make that negative as well. Are we done? What do you think? Are we done expanding this? No. There is still more we can do to expand this. This is okay, but not that one, because that one has an exponent. We can bring that exponent down and in front, and then we'll be done. So equals 2 log of x to base a minus log of y to base a minus 3, right? The 3 came down and in front, log of z to base a. There is the full expansion of that expression that we began with. Okay? All right, so let's look at that, the next problem. Again, please pause the video, answer this question, and then come back to the video after you have your own solution figured out. Okay? So I'm assuming you've done that. Now you're back. Welcome. Welcome back. So this is a division problem. That means we can rewrite it as a subtraction problem, right? So let's do that because we're expanding it. So this is equal to natural log of x cubed times square root of x minus 1 minus natural log of 3x plus 4. Right? So far so good. Now that is fine. But what about this? I mean, now we have a subtraction, that's fine. But look at the inside of here. There's nothing we can do more, we can do to expand this any more than what it is. But how about this one? This one we can, right? You have the log of product of two terms. And we know when we have log or natural log, natural log. So if we have natural log of product of two terms, we can expand it and make it into an addition of two terms, right? So we can go this way or that way. We're going this way because we're expanding things, not combining them. So we can say natural log of x cubed plus natural log of square root of x minus 1 minus natural log of 3x plus 4. Look at that. They ask us to expand this, and we're certainly doing that. Okay? So the next step, this is fine. How about this? Can we do anything to expand that first term? We can, right? Just bring this power down and in front. So 3 times natural log of x. How about this? Can we do anything to expand this? We can, right? Just rewrite it. First, we have to rewrite this with a rational exponent. So let's convert this radical to a rational exponent. So plus natural log of x minus 1 to 1/2 power minus natural log of 3x plus 4. Okay? Certainly now we can expand this a little more. These two are fine. These two terms are expanded as far as they can go, but not the middle term. The middle term, we have this exponent. We can bring it down and in front. Right? So let's do that. 3 natural log of x plus 1/2 natural log of x minus 1 minus natural log of 3x plus 4. Okay, so can we expand any of these terms any further? No, that's as far as we can take these. So we have fully expanded that expression, and this is our final answer. Okay. Moving forward. Look at this. We're still expanding. Okay. I'm hoping that you've already solved this one and you're here to see my solution. If not, it's easy. Just pause the video, use your own scratch paper, solve this, expand it as much as you can, and then come back to the video. Okay, I'm assuming you've done that. Welcome back. So let's see. The first thing we would do, we would write this radical expression in terms of a rational exponent. So that is equal to natural log of all of this on the inside, which is 8 times r to 7th power s. All of the inside has power 1, right? The index here this time is 4. So 1 divided by 4. Okay? Again, all of the inside has power 1. If you take them all together, they have power 1 as a whole. The index is 4, so we can rewrite the radical as 8r to the 7th power times s to 1 over 4 power. Now, we know that this power can be brought down and in front. So let's do that. 1/4 natural log of 8 times r to 7 times s. Look at that. We have plenty to do here, right? We have 8 times r to the 7 times s. So we can convert the multiplication to an addition problem. But be very careful, because as you do that, as you expand what's inside the parentheses, you're going to end up with 3 terms. Now we have 1 term. 1 term multiplied by 1/4. When you expand this, you end up with 3 terms. So all those 3 terms must be multiplied by this 1/4. This 1/4 belongs not only to this version of the natural log, but all of its expansions after we do it. So this 1/4 belongs to this and any expansions of this. So what do I mean by that? I mean, when you say 1/4, before you expand this, again, you got to put that red bracket indicating that this 1/4 is going to distribute itself to all the 3 expansions. Okay, now we can write natural log of 8 plus natural log of r to the 7 plus natural log of s. Now we close the bracket, right? This 1/4 belongs to all of this. That means if you expand this, this 1/4 belongs to all of those expansions. So there, 1/4 now multiplies itself or distributes itself to all the 3 terms. If you forgot to do that, you're going to end up with 1/4 times natural log of 8 and the other 2 not getting or receiving this 1/4 as a product, which would be totally wrong. Okay? All right. So now, is there anything we can do on the inside to expand it a little more? Yes. These 2 are fine, but not this one. This one has an exponent. We can bring this exponent down and in front. So 1/4 natural log of 8 plus 7 natural log of r plus natural log of s. right? S. Is there anything else we can do to expand this? Absolutely. We have to distribute the 1/4. Remember, we're making this expression bigger and bigger. So we need to distribute. So equals 1/4 natural log of 8 plus 7/4 natural log of r plus 1/4 natural log of s. Okay, is there anything else to expand this? No, this is the full expansion of that original expansion, that original natural log expression. So compare that with its expansion. Okay. Okay, this one. Again, please pause the video if you haven't done this already and solve this. Expand this, then come back to the video. All right. I'm assuming you've done that. So here we have the natural log of the product of two terms, right? And we learned earlier on this sheet that natural log of the product of two terms can be written as the natural log of the sum of those two terms, like that. So let's do that. Natural log of x plus natural log of square root of y over z, right? That's the first step. Is there anything we can do to this to expand it anymore? No, this is fine. How about this? Yes, there's a lot we can do here. So let's do that. First of all, let's use the properties of radical expressions and distribute this radical to numerator and denominator separately. So we can write natural log of x plus natural log of square root of y divided by square root of z. Okay. Now we know that using this property, we can convert a division, log of a division of, or natural log of division of two terms to be equal to natural log of the subtraction, natural log of numerator minus natural log of the denominator, right? We have that property. Let's apply it. So we have natural log of x plus, there is no coefficient here, so we don't have to put a red bracket indicating that that coefficient belongs to the full expansion. So it's just 1, so we don't worry about that. Plus natural log of square root of y minus natural log of square root of z. Okay. Is there anything else we can do to expand this expression? Absolutely. Let's rewrite these two in terms of rational exponents. So natural log of x plus natural log of y to 1/2 power minus natural log of z to 1/2 power. What about now? What do we do now? Well, you have a power. We can bring it down and in front. Okay, so let's do that. So that is equal to natural log of x plus 1/2 natural log of y minus 1/2 natural log of z. Is there anything else we can do to expand this? No. That's all we can do. So let's box this as our final answer. Okay. Please make sure that you do continue solving these problems on your own before you look at the solutions of problems in the book, before looking at or watching these solutions that I give in the videos. And that's critical. That's critical to learning math. If you skip that step, then you'll say, well, I'm not good at math. Why do I wonder why am I not able to solve these? Well, because you should not skip writing down your own solution. It's a critical step in learning all quantitative subjects, not just math, all the other ones. And I know I've said this before, but I keep saying it because a lot of my students They are very capable of doing mathematics, it's just they don't know how to study it. Okay, so please make sure that you review these problems again without looking at the solutions and trying to get those answers on your own. We have come to the conclusion of another section, and thank you for persisting through this video. For now, have a nice day, and I'll see you all next time.